All right, so let's move forward. Now we need to talk about bonds. So we have three types of bonds that you need to understand. Ionic bonds, which we'll get to today. Covalent bonds, which we will also get to today. And then within covalent bonds, we have polar versus nonpolar bonds. This we are going to save for Wednesday. But then we also have hydrogen bonds. So once you understand polar and nonpolar bonds, you can start to understand hydrogen bonds. And these are all ways that elements or atoms are brought together to work together as in a molecule. All right, so let's talk about ionic bonds. We already talked about what an ion is. An ion is created when an atom either gains an electron, and if it gains the electron, remember it's going to be negatively charged, or if the atom loses an electron, in which case it'll be positive charge. Over here, we tend to gain an electron and get a negative charge. Over here, we tend to lose an electron and have a positive charge. Now, when that happens, these are going to be attracted together. So remember, opposite charges attract. So a positive charge is going to be attracted to a negative charge. And so when that happens, chlorine with its negative charge will be attracted to sodium with its positive charge, and what you end up with is sodium chloride. That's an ionic bond. So ionic bonds are usually between our metals over here, because our metals become positively charged, and our nonmetals over here, which usually become negatively charged. All right, this is an extreme difference in electronegativity, which we'll talk about tomorrow, but basically one is going to, over here we're so close to having our shell filled that we're going to just basically grab an extra electron. And over here, that extra electron in sodium is held on so loosely, it's more than happy to get rid of it. And so when that happens, those two become opposite charged and come together. So those opposite charges attract. And one more definition for you is an anion is a negatively charged ion, and a cation is a positively charged ion. So go ahead and answer on Edpuzzle. Give me one example of an anion and one example of a cation. All right, your anions are going to be mostly over here, are these over here, and your cations are these over here. And so when that happens, so here we have chlorine. Now remember, chlorine should have 3 shells, right? Look at it here. It has 1 shell with 2, then a shell with 8, and then it has 7 of the 8 in its third shell. And we can see that here. There's its inner shell with 2, second shell with all 8, and then the third shell has 7. 1, 2, 3, 4, 5, 6, 7. So what's its valence? Its valence is 1. So it's going to often gain an extra electron and then have its negative charge. Sodium, on the other hand, here we have sodium, and if we go back to the periodic table, you can see that sodium has 3 shells, 2, 8, and then only 1 in its third shell. And that 1 is very loosely held because sodium is going to try and get to that octet again. And so when chlorine interacts with sodium, chlorine is so strongly attracted to trying to get that extra electron, it'll often steal it completely. This is not sharing this electron, this is stealing it completely. And so sodium now has a positive charge because it lost its outer electron, but it's happy because it has the octet rule. It has a positive charge, but its octet rule is full. Its outer shell is full. Now chlorine is also happy with its negative charge because its outer shell is full. And what do opposite charges do? They attract. So the sodium is going to bind to the chlorine, and it does this in this cube form, because if we were to cut this open, you would see that each sodium has 6 negative charges around it. There's a chlorine, there's a chlorine, there's a chlorine, there's a chlorine. There would be 1 chlorine inside and another chlorine going to form outside. So inside this molecule, sodium is surrounded on all sides with a negatively charged chlorine. And chlorine is the same way. Each of these chlorine is surrounded by a sodium. Sodium, 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 sodium inside, sodium outside. So each negative charge is surrounded by 6 positive charges, and each positive charge is surrounded by 6 negative charges, and that basically holds all of these together. Those opposite charges hold these together and eventually make your salt crystal. Salt is sodium chloride, NaCl. One thing to really remember, though, is that that is relatively weak. What happens to salt if we put it in water? Well, the salt dissolves, right? The reason salt dissolves, and we're going to learn all about this tomorrow with polar bonds and so forth, but the reason salt dissolves is because Water also has some charges. These are only partial charges, not full charges, but the partial charge of water is happy to interact with the positive charge of sodium. So oxygen has a partial negative charge that will interact with the sodium. The hydrogens on water have a partial positive charge that will happily interact with the chlorine ions. And when that happens, the water basically can just pull those sodium ions out of this crystal, pull the chlorine ions out of this crystal, because the sodium is still happily surrounded by 6 waters with the negatively charged dipole oxygen near it, and chlorine's happily surrounded by 6 waters, but with the positive dipole hydrogen around it. So we know that ionic bonds are relatively weak because they can be broken by water. And we'll learn a lot more about why that's the case on Wednesday. So bring your questions there too. All right, so then covalent bonds. Remember how we talked about valence? All right, so real quick, go ahead and answer a couple questions on the valence of carbon, the valence of oxygen. So for these guys over here that aren't real close to having their outer shell full, and they're therefore probably not going to create an ionic bond with the metals over here, things like carbon, nitrogen, oxygen, they fill their outer shell by sharing electrons, often with each other. Right? So a covalent bond is a shared pair of electrons. This is very strong. Covalent bonds basically need enzymes to make or break them. So these are very strong. And we have polar and nonpolar versions, which we're going to get to in a little bit. When you see a molecule drawn like this, carbon, hydrogen, remember carbon has a valence of 4, hydrogen has a valence of 1. This is a molecule it forms because this allows carbon to have 4 bonds and therefore share and gain 4 of its electrons. Oxygen, what was oxygen's valence? 2. That's why oxygen only binds to 2 hydrogens, H2O. There's our water. So let's take a look at this by drawing in some actual ions or electrons here. So I'm going to ignore the inner shells because those are happy, those are full. But this outer shell of carbon, remember, basically had 4 electrons. Let's see if I can get my pen working here. All right, so it had 4 electrons in its outer shell. It was not fully happy. It wants to have 8. Now, each of these hydrogen brought their own 4. So this one was from hydrogen. This one was from hydrogen. This one was from that hydrogen. And this one was from this hydrogen. So now, if carbon is sharing those electrons with hydrogen, each of these hydrogens basically has 2 now. So each of these hydrogens has 2 because it's sharing that one that came from carbon. But carbon actually itself has 8 because carbon is sharing this hydrogen's electron, this hydrogen's electron, this hydrogen's electron, this hydrogen's electron. Its outer shell now has 8, and that's how this works. So oxygen basically already had 2 of its outer shell paired because it had 6. So it had 1, 2, 3, 4, but then it had these, number 5 and number 6, without a pair. So it's going to bind with hydrogen, which contributes its electron, and now everyone's happy. Hydrogen has 2, oxygen has 8 because it made 2 bonds. So let's take a look at this with fluorine. How many bonds does fluorine need to make? Well, obviously fluorine needs to make 1 bond. Its valence is 1. It has 1 unpaired electron. So in comes hydrogen with its 1 electron. They are going to share those electrons. So this pair of electrons here is now shared between hydrogen and fluorine, and this is a molecule of hydrogen fluoride. Now hydrogen fluoride is at pretty close to being an ionic, that's why it's an acid. They break apart pretty easily, but this is the idea of the shared pairs. So what's the valence of nitrogen? I think I've asked this a few times before. So how many bonds would nitrogen make? Let's take a look at this element. What is this element? Well, what you look at here is the nucleus. So what is this element? Well, if the nucleus has 8 protons, this element is oxygen. And here we can see oxygen, as we would expect, has 6 in the outer shell, the outermost shell. Its valence is 2. It needs 2 more. Here's another oxygen. That can come in and create a double bond. Oxygen is going to share both of these electrons with the next oxygen, and that's a double bond. But both of these oxygens are now happy because both have 8. 1, 2, 3, 4, 5, 6, 7, and 8. 2 of these shared ones came from this oxygen by itself, and then 2 are borrowed from this other one. But this oxygen is also happy because it has 8 as well. Right? And then here we get to water. Here's oxygen with its 6 outer shell electrons, valence of 2, hydrogen needing 1, and so the oxygen and the hydrogens are going to bind. There's dihydrogen monoxide, 2 hydrogens for 1 oxygen. There is water, H2O. And now everyone's happy because their outer shell is filled. This sharing of electron is a covalent bond, and that is a very, very strong bond. It is virtually impossible to break water apart into hydrogen and oxygen separate. All right, so at this, we're going to come back on Wednesday and talk about electronegativity and how oxygen gets the negative dipole that we mentioned briefly, how these hydrogens gain the positive dipole, and what this means with regards to hydrophobicity and hydrophilicity.